Hello and welcome to this clip going through a evaluative task paper from the previous specification, previous meaning 2008-2015 OCR chemistry website, and it's about water crystallization, but specifically how to work it out using redox titrations. Now the evaluative task that used to be set is quite similar to some of the practical type questions you'll get in the current papers for the OCR Chemistry A 2015 onwards specification. So in carrying out this exercise, we'll go through how you can evaluate a procedure as you go, as well as actually using the data to calculate a value such as the value for X in XH2O. So the first thing to look at is any data that might be of use to you. So it describes what the student did. They tried to find the value of X in hydrated iron 2 nitrate by two methods, by first of all doing a redox titration and by secondly doing displacement. So the displacement in this case isn't just the displacement that you might remember from GCSE. This time we're using electrochemical data to work out which is a more reactive metal that might achieve this process for us. So it says the student first prepared an aqueous solution by dissolving 3.60 grams of the hydrated iron sulfate in water. And in the titration, it says the solution was acidified and then titrated with a standard solution of potassium manganate 7. So this is obviously drawing on your knowledge of the iron 2 plus manganate reaction. It comes up quite a lot in redox titrations. So the key thing to remember is it's a 5:1 mole ratio. So 5 Fe2 pluses are needed to reduce 1 MnO4. So moving the page down a bit, we can look at the displacement part. So the two highlighted sections tell you exactly what happened, and you've got the electrochemical data. So to do this, you need to choose a metal whose electrode potential is more negative than that of Fe2 plus / Fe, and therefore Fe2 plus will be reduced to Fe, displacing the iron. Now you've probably been a bit quicker than me to spot a misprint there. It is a specimen paper after all, and occasionally mistakes find their way onto them. Obviously that's got to be aluminium, not zinc. Aluminium can't suddenly turn into zinc by gaining 3 electrons to an aluminium 3 plus ion. So you can see already that there's two possible candidates, either aluminium or chromium, because their electrode potential values are more negative than that of the iron. So therefore the iron 2 plus will tend to be reduced in their presence down to Fe solid. So let's go on to the next page and get the work started. So the first thing to do is to look at the question is asking you to decide on a suitable metal that could be used for the displacement reaction. Now we've already looked at either aluminium or chromium. I'm happy to do aluminium in my answer. So I've chosen aluminium for my first mark. I've used the electrode potential data to justify it for my second mark. Now I need to do an equation. So because Fe2 plus Fe has the more positive of the two electrode potentials, you reverse the aluminium half equation and you multiply up accordingly so that you have the same number of electrons. Just making sure my electrons have a negative charge there. So now you can cancel through, and that gives you the equation. So now what we need to do is to go on to the next part. So moving the page down, it says in the displacement experiment 0.00125 moles of Fe was obtained. And it asks you to use that amount of Fe to help you calculate the value of X in FeNO3-2XH2O. So looking at the beginning part of the question, it tells you that there's 3.60 grams of your hydrated iron nitrate salt. We know the mass, but we don't know the molar mass because it's unknown due to X. However, it does in the equation tell us that, in the formula, that for every 1 mole of FeNO3-2XH2O, there's 1 mole of Fe. So therefore we can use that information to ascertain that there's 0.00125 moles. So in your full 250 centimeters cubed of hydrated iron nitrate solution, from which you used 25 centimeters cubed to do the displacement, that must mean you multiply 0.00125 times 10 to make 0.0125 moles of your hydrated salt. So rearranging moles equals mass over MR, that gives us 288 grams per mole for our hydrated iron salt. So if we take the anhydrous salt, so take away the XH2O, we have 179.8 grams per mole. So the difference between the molar mass of the hydrated salt and the molar mass of the anhydrous salt gives us the number of grams of water that are present, assuming 1 whole mole, of course. So divide that by 18, and that gives us 6 moles of water. So therefore, 6 is the value of X. So moving on to the next part of the question, you can see that now they're asking you to try and make some improvements or make some comment on the reliability and accuracy of the two methods. So it says the titration method gives a more reliable and accurate result for X than the displacement method. It says explain and state 2 reasons for this. So when you do the displacement, you only carry out the experiment once, as opposed to several times when you do a titration. So you don't have the same reliability. You can't tell if it's repeatable or not. And with the top pan balance, it's used twice per weighing. So the empty weighing bottle plus the weighing bottle and iron combined, that doubles the overall error because you're implying the same percentage uncertainty twice. So therefore, the top pan balance is a more inaccurate way of deciding this because there's a greater percentage uncertainty applied. So then it asks you for 2 modifications to the displacement reaction that would produce more reliable and accurate results. So, in the same way that you do repeat titrations to get concordancy, and you also keep weighing until you get constant mass when you're doing water crystallization measurements by heating, you can repeat the displacement until you get consistent results, so that the principle is the same. And if you use a more accurate balance, this will start to offset the negative effect of having to use the balance twice for each mass measurement, because the mass measurement is taken by difference. So each time you do a mass measurement by difference, you have to take 2 readings, which introduces the error twice. So let's now move on to the next part of the question. So it then says in part D that the value of X could also be worked out by heating the hydrated compound to drive off the water crystallization to obtain anhydrous iron nitrate, or iron 2 nitrate. So you'd have done this in your first year. Now the difficulty with that is the iron 2 nitrate further decomposes according to the equation 2.1 that they give you. And therefore it says some of the anhydrous iron 2 nitrate is likely to do this. So you need to think about the most likely effect of further decomposition like this on the value of X obtained. So what will happen is X will be increased because the loss of nitrogen dioxide and oxygen gases could also be mistaken for additional water loss. So the total loss of the mass that you measure will be greater than the loss of the mass that's due to the H2O only, which is what you're trying to identify. Then it says a student suggested that this approach could still be used to obtain an accurate value of X by strongly heating the hydrated iron nitrate until it all decomposed into iron 2 oxide. And it says explain with a reason whether you agree. So the student is actually correct, because if you assume total decomposition, then the only remaining thing in the pot will be FeO, in the crucible, will be the iron oxide. So both equations together can be used to eliminate, using molar ratios, the amount of NO2 and the amount of half O2. So therefore you can leave the remaining, or the NH2O that was actually lost initially. So moving the page down, it says the iron 2 oxide readily oxidizes in air to form iron 3 oxide. So this reaction takes place slowly. So it asks you then to think about the effect on the value of X obtained if some of the iron 2 oxide was oxidized, and to explain what you mean. So X would be smaller this time because the oxidation being described would involve adding oxygen from the air, meaning the difference in the mass that you measure would actually be lower. Okay, so going on to the final part of the question. So in part E, it has another possibility, another modification you could do, would be to work out the mass of water that was released. Now obviously, the water is actually released as a gas, because you're heating the hydrated salt strongly. So you need to think about how we could collect this. Now normally you'd not heat a solid using this apparatus, but it asks you to draw a label diagram to show how this could be carried out experimentally. So normally this looks like a distillation apparatus, which it is. Now distillation usually takes place to separate liquids. So this time you're trying to get rid of the gas from the water as a vapor from the hydrated salt, and then collect it again. So you're actually allowed to use any one of a number of possibilities here, provided you're actually showing how the water could be collected. So using a condenser to actually collect the water accurately is the most important part. So I've highlighted the bit that's possibly quite important, and there's several possible options for what you could use to actually heat the iron nitrate, the hydrated version. So if you could somehow attach a condenser to another type of container where you're heating it and allowing it to escape and get into the condenser, that would be what they're after. And it's important to point out as well that the system isn't closed because the water vapor can escape to the condenser and then be turned back into water as a liquid and then weighed, or the mass recorded. So, moving the page down, the student suggested that any further decomposition, as in the equation earlier, would then not matter using this modification. So the student's right, because the decomposition takes place in the flask on the left-hand side of the apparatus, and the value of X is calculated from the collected water on the right. So because the two things have been separated by this apparatus, that means that the level of decomposition or the extent of decomposition further in the flask doesn't really matter, because the water has been collected anyway. Okay, so hopefully you found this a useful roundup of this question. It was quite a hard question, quite demanding, but it's interesting and useful because it gets you to really think about how an experiment is designed. It gets you to think about the rationale behind the different methods that we use when we're doing experiments, and it has some relevance to what we've been doing lately with electropotentials and redox. Okay, so for now, thanks for listening, and until next time, see you soon.